Good morning, teachers. I am Rishabh Singh from College Sri Lanka Institute of Technology, Tumkur, Karnataka, and I am doing in embedded. I have done embedded system internship at Emertxe and the EI25 underscore 014, and this is my email address. And the project we have done here is microwave oven. The overview of this internship at Emertix has focused on the embedded system designs, and this has given me the hands-on training with the microcontroller programming, how to do peripheral interfacing, and how we can head to the real-time applications. So I have developed a complete micro controller project using the controller PIC16F877A. So I have gained experience in the coding and how to handle interrupts and state machine designs. And I have built a demo-ready embedded system with integrating the LCD interface, then keypad input and timer-based countdowns and fan controls. Now heading to the next subject, that is goals of internship. And the goals of internship is it has strengthened the fundamentals in the embedded system programming and the microcontroller architectures. I was also given the hands-on experience with how to interface the LCDs, keeper timers and interrupts, and how to merge them all together. And I have learned to design and implement the real-world applications. So I have developed a good skills in coding, debugging, and testing. I've also known how to move from the demo-based project to the real-world embedded system projects, and this has built confidence in presenting the technical work with clarity and to think at the product level. These were the goals of internship. Requirements of the project, which is being required. We have to implement a microwave oven controller using PIC16F877A microcontroller, and we have to provide a user interface with 16 cross 4 LCD and the matrix keypad of dimension 4 cross 3. We have to provide multiple cooking modes such as micro mode, grill mode, convection mode, and the start mode. We will also implement time settings in minutes and seconds, and also temperature settings for the convection mode. That is the third mode in the cooking mode, and we will also include preheating functionality before the convection cooking start. We will also give fan operations to simulate the heating process. We will also give timer to interrupts for precise 1 second countdown. We will give the options for pause, stop, and the resume cookings, and we will display clear messages what is happening in the project and at what stage that embedded system is. Like it is, it will display the messages if on the LCD for the timer countdowns and in which mode it is for the user feedback. Now, coming to the next, we will be starting our introduction to C. So C is a structural and general purpose programming language. It is very portable, means it can run on the various devices. It is not made for a single device. It is efficient and widely used in the system software and embedded systems. Its key strength is it is very close to the hardware, and it also supports structural programming. Let us see one of the examples of C. First of all, we have included stdioh.file. This is a preprocessor directive, and it includes standard input-output library. Then here is our main function starts, and we have defined some of the integers such as 5 and 3, and int is the data type of integer. So we have declared and initialized variables here. We have also calculated the sum, and we have printed the sum on the output screen, and we have returned 0 at last. That represents the exit of the program, and it represents successful exit of the program. So heading to the basic data types, we have three basic data types: char, integer, float, and double. So char stores single characters like A, B, C, D, like that. Integer store integers and the whole numbers like 1, 2, 3, 4, or 50, 60, 100. Float and double are used to store the decimal values. Float is of 4 byte size, and double is of 8 byte size. So if we have to store very large values, then we go for double. Now coming to the conditional statements used in C is are if else, and if else if. The conditional statements are, what does it mean? Based on a certain condition, whenever a condition is met, we will run a certain set of statements, and then we use conditional statements, and these statements are used in the decision making processes. Another conditional statements are switch, which are for the multi-way branching. It means Based on a certain condition, there are few cases there, and whichever case the input matches, that expression matches, that case will run. Else a default case is also there that will run when no case will match. And there are certain loops in the conditional statements such as while loop and do while loop and the for loop for the repetition of the task. While loop runs until and unless the condition is false. Similarly, do while and for loop is run. The basic difference between while and do while is do while uh, runs for at least once, while whereas the while can break out at the first time only. So these are used for the control program flow. The next topic in the introduction in C language is the arrays. So arrays is basically a collection of the data of the same data types. It is not of the variable data types, it is of the same data. So we have defined a syntax here that giving the data type, the name and size, where size is the number of elements that are contained in that variable array, and the net size of that variable will be size into size of the data type. Example, we have defined integer age here. We have given 5 ages, and so the size of the age variable is 5, but the net size of the array age variable will be 5 into 4, whereas where 4 is the date uh, where 4 is the size taken by the individual integers, and we can access each value of this array variable by using indexes. The next is a pointer. Pointer is a variable that stores the memory address of another variable, and we use pointers because these are very powerful because they allow direct memory access and manipulations, which is essential for very efficient programming. And here is an example of a pointer. First of all, we have included a standard library, then we have defined initialized variable x. We have defined pointer, and this is represented by star. So we have initialized a pointer star ptr. We have given value x 5 to we have given 5 in x, as we can see in the block diagram, and the address in the memory was assigned was 1000 by the compiler, and we have passed that this address to the pointer. So we can say here the address of 5 is getting stored in this pointer. And we can also dereference this pointer. Dereferencing means we can fetch again 5 by using this 1000. We will write, if we write star ptr, then it will fetch the value stored at the memory address stored in this pointer. Next, coming to the functions. The functions are the modular blocks of code that are used to perform very specific tasks, and here we use functions because whenever we have to do some of the specific tasks at the some specific times, then we declared functions out of the main function and we call them in the main function. One of the example is mentioned here is, first of all, we have initialized x and y. We have given value 2 in x, and then we have made a function foo, and we have passed x in it. We have initialized ret equal to 0, and the value of ret will be x plus 1. So value of ret will be 3 now, and 3 will be stored in y. And if we print using the printf statement, then it will print y is 3. Next, coming to the strings. Strings are the continuous sequence of characters, and the end of a string is marked with a null character with a single quotation marks with backslash 0. And here are few programs representing the strings. Here, let us say we have initialized strings here. We will initialize the string with the char data type, and with after the variable we will use this square brackets. So let us suppose we have written gigs here, and for printing we will use the format specifier as percentage s. So the at last output will be the string is gigs. We can access any character by using their indexes. So let us suppose we want to access the first character, then we will go at the 0th index and we will print it, and that's why it will print G. We can also update strings in it. For that we have to go to that index and we can replace it. Example, here we have initialized defined str uh, string as geeks, but later on we wanted to change this first element. So we'll go to the 0th index and we'll replace, suppose we are replacing by r, and if to check whether it is replaced or not, we'll print it using the percentage format specifier, and it has printed R in it. Now heading to the next topic, storage classes. So since we know that the Linux operating system is divided into two major sections, user space and the kernel space. As the name suggests, user space is defined only for the users and kernel space is not defined for the users. So whenever any user program is getting trying to get access for the kernel space, it will lead to the segment violations. And the storage classes define scope, lifetime, and visibility of variables. And there are certain types of storage classes as auto, static, register, and async. Give, I will give an example here, like a static int count. It returns the value across all the function calls because here static keyword is there. It keeps the value variable in of that variable in all the function calls. The next one is the preprocessor directive, and these are the commands which has to get run before the compilations. And without any preprocessor directive, we cannot write any C program. And the methods to include them in the program is by using include keyword. So I will write hashtag include stdio.h. Stdio.h is for the basic input output commands. And this preprocessor directive also supports macros like defining any variable outside the main function. Topic introduction to embedded systems. So I will define the embedded system definition. This is a combination of a hardware and software which is defined and which is made and intended to do a specific task. We can see this type of system in cars like automatic braking systems and in aeroplanes and televisions. There are certain categories of embedded systems we have. The first one is the standalone embedded systems. As the name suggests, it works independently without needing any host computer. So it just takes the input, processes it, and gives the output directly. It do not need any control from the another computer. And we can see this type of embedded systems in washing machine and microwave oven controllers. The next embedded system is the real-time embedded systems. These are defined to respond within the strict times. So based on this, there are two types of real-time embedded system. First one is the hard real-time, and thus there in this if the processor has to do that specific task within the stipulated time, and if it fails to do that, then it is said as a system failure. Example we can see in the aircraft controls. And the second one is the soft real-time systems. Here also that deadline is important, but occasional delays can be tolerated, like video streaming. Now coming to the next, as the next category as network embedded systems, and these are connected to the networks. As we know, the networks such as LAN, WAN, or the internet, and these embedded systems are designed to communicate with each other devices for exchange of data and also for the remote control. We can see these types in industrial automation systems and in smart home IoT devices. The last category is the mobile embedded systems. This is the simplest one, which is optimized for low power and mobility, and these are used in portable devices, example smartphones and tablets. So as I have already said, that embedded system is a combination of software and hardware. So these are the components. So any software can be developed, and according to the hardware, it can any project or product can be implemented. So basically, we know that to sense any data from the environment which are analog in nature, we have sensors, and to convert that analog data to the digital data, we need analog to digital converters. Based on this sensor, if any action to be performed, we need actuators for that. And for powering up the system, we need power, and the cooling system we need so that the controller board could not go much at higher temperatures and could not melt down the wirings. So here, this part is the main brain, where it can be a microprocessor or a system on chip or a microcontroller. And we need a memory also, where the software will be stored for permanently, and where random access memories in random access memory, the temporary calculations will be done. We also need other systems like FPGA, diagnostic port, and human interfaces. Better system requirements, it should be reliable. It means it should perform the intended function correctly and should not give any failures, because if failures in the embedded system can be critical, and they are always come in the market after rigorous testing and fault tolerances and seeing all these issues. Then embedded systems have low power consumption because many embedded system runs on batteries and limited power sources, example mobile phones, PC. And there should be an efficient use of memory because memory is limited in the embedded devices. So programs should be compact, It should avoid wastage of spaces, and the data should be managed very carefully. Next is the real-time aspects of the embedded system. In these three categories are the hard real-time, firm real-time, and the software real-time embedded systems. In the hard real-time embedded system, as we can see from the name, the processor or the microcontroller should do the specific task within the given deadline. If given deadline without fail, example pacemakers. If the pacemaker do not generate electric pulses, then patient can die. Or anti-lock braking system is also an example of hard real-time embedded systems because the failure to apply brakes automatically can result in the accidents. The next one is the firm real-time system. It is similar to the hard real-time system, but occasional deadline deadline misses can be tolerated, and this type of embedded systems is seen in telecommunication switching. The next is the software real-time systems. In this also deadlines are important, but the system can tolerate certain delays, not always. And here if the failure here if it fails to do that, then here the performance will degrade. And there are certain types of examples we can see in video streaming and online gaming. So heading to the next topic, that is types of memory. There are two types of memory. First one is the random access memory, that is RAM, and the second one is ROM, that is read-only memory. So RAM is the volatile type of memory. It means when the power is switched off, the contents will be lost from the RAM. But this is used for the faster access for the temporary calculations, and it includes read and write cycles. Uh, and there are so many read and write cycles are allowed. And there are two types of RAM, static RAM and dynamic RAM. The static RAM one is much faster, but it is a bit expensive, and here no refresh cycles are required. The dynamic RAM is cheaper, but it is slower because it needs some periodic refreshes of the cycles, else the memory from the DRM will get deleted and it won't retain the data. The second type of memory is ROM, that is read-only memory. And the thing here is when the power is switched off, it will retain the data, and therefore it is used for the permanent storage in firmwares. Traditionally, whatever the ROM were developed, they cannot be modified, but from the today technological things, we can modify the ROM, and so we will see the types of ROM now. Here are the certain types of ROM we can see. So the first one is the mask ROM. It is the mask ROM is program. Every type of ROM is programmed during manufacturing, and this mask ROM is one of the cheapest one, and this cannot be modified. This cannot be changed after it has come to the market. The second one is the PROM, that is programmable read-only memory, and this can be only programmed only once, and that's why it is also known as one-time programmable. Third category is the erasable programmable read-only memory, and it can be erased using UV lights, and then it can be reprogrammed with certain other data. The next one is the electrically erasable PROM, and it can be erased and reprogrammed using electricity. And it supports multiple write cycles. Instead of in PROM, we could have only edited the firmware for the one time, but in EPROM, we can it supports multiple write cycles. The last one is the flash memory, which is used in the modern devices. It's very fast, and but it do not support bit by bit erasable of the data. It supports it erases the data in blocks, and it is widely used in the microcontrollers for firmware storages. Now we will see the certain types of flash memory. There are two types of flash memory. First is the NOR and the second one is the NAND flash. Both are the non-volatile memory, so when the power is off, they both will retain the data. And the differences between the write cycle is in both we can the data can be written or erased. But in NAND, we can do that it for the more number of times, but still the number is finite. And for the read cycle, in both, we can read the data in finite number of times. But the NOR flash is suited for mainly for the firmware storages and the boot codes or the BIOSes. But the NAND flash is used for the mass storages in SSDs or the USB drivers. Coming to the that is introduction to microcontrollers. So the definition of a microcontroller is it is a compact integrated circuit, and it is designed to govern a specific operation in the embedded system. So for every embedded system, uh, a different type of IC is designed, a different type of microcontroller is designed, and its core components is the CPU, which is the main brain of the microcontroller, is used for executing the instructions. And to execute these instructions, we need memory to store ROM and the RAM data. We also need input and output ports which connect to the sensor and actuators or the displays. And we and for and so that all can be integrated, we need timers and counters to manage precise delays and the events. Now there is a difference between a microprocessor and a microcontroller. The microcontroller is an integrated circuit where all the CPUs, RAM, ROM, timers, input/output ports are integrated on a single board. Uh, and but it is different from a microprocessor because in the microprocessor is a general CPU and it needs external components to function. It do not come with the external components, and we need to combine external component with it manually. So the cost of a microcontroller is lower cost and they are low power consumptions, and their applications are in the washing machines, microwave ovens, and the remote controls, whereas the applications of microprocessor are in PCs and laptops we use. Now we will see the general architectures. The first one is the von Neumann architecture and the second one is the Howard architecture. In the von Neumann architecture, it uses a single bus to fetch both the instructions and the data. So the CPU must wait if the CPU and the data both the access of to both collides. Whereas in the Howard architecture is a better one. It supports a memory for both instructions and data, and it uses two buses. One is for the instruction, second one is for the data. So it allows parallel access to the CPU, and therefore it is more faster and more efficient in the embedded systems. Now, moving to the project, and the microcontroller which we are using in this project is the PIC16F877A, and we will be discussing about this and whatever the data that I have taken is from the data sheets and from the web services. The first one we will discuss about the ports. So it has five ports: port A, B, C, D, and E, and these ports can be configurable as input and output ports, and these are the data direction register ports, and it controls the flow of the data, where the data should go in or go out. The second one is the LEDs. LEDs can be controlled via port pins that we will see in our project, and they are commonly used for status indications, powering on, or the cooking mode. The third one is the character LCDs. These are the short form is CLCD. These are used for displaying the messages or the menu. And there are 16 pins on the LCD that we can see in the figure. And it will be discussed, every detail of this will be discussed in the projects. And we have two types of CLCDs that we can use in this microcontroller is 16 cross 2 or 16 cross 4. In 16 cross 2 there will be 16 vertical lines and two rows, and in 16 cross 4 there will be 16 vertical lines and four rows. Are the data direction registers, and this data direction registers in a microcontroller is used to configure the pin as input or output. If we assign the trace registers as 0, then it will be an output, and if we assign it 1, then we can give input to the registers. The next one is the port registers. These registers actually store the data and they control the logic levels as high or low. So when we give high, it drives the logic level high, and when it is given, it drives the logic level to low. The next one is the watchdog timer. So a watchdog timer is very important in micro and the embedded systems. It is a hardware timer which is built in the microcontrollers, and its purpose is to detect and recover from any software malfunctioning if the watchdog timer detects. So it continuously countdowns from a preset value, and if the program is not resetting the watchdog timer from the preset value, then the microcontroller will reset the program automatically. Coming to the main project, that is microwave oven. First of all, I will give a brief overview of this project about what are all the header files included and all the source files included in this, and at last we will go to the simulation part. Here in the timers.h, there are two timer initialization, timer 0 and timer 2. And in the CLCD header file, the header file defines all the macros and the constant and the function prototype to have a control on 16 cross 4 LCD display. So here from the data sheet we have taken this diagram. and there are 16 pins. There are 16 vertical columns to control the LCD. First of all, we have defined here the actual frequency, that is oscillator frequency, to 20 megahertz, and we have also set up the pin configuration. For the data lines, we have used 4D as the LCD data lines, and register select as RE2 and enable pin as RE1. And in the modes, since we know there are two types of modes, instruction mode and a data mode. Instruction mode is used to send the commands, and data mode is used to send the characters. And there are two logic levels defined, high and low. And to go to the lines, we need addresses which are calculated in DDRM addresses for cursor positioning as line 1, line 2, line 3, and line 4. Moving to the uh, next part is we have also defined LCD command macros of 8-bit mode, then 4-bit mode, then two lines. In the initialization part, we have also defined macros for clearing screen, display and on off, for turning on the cursor and off, and bar for the solid block of characters. Because at the end of the when we will start simulating, it has to write powering on, and above that it will display bars. So we have defined macros for that bars. Now, the function prototypes defined as for the CLCD as init CLCD, we are initializing CLCD here, and also we have defined function to for printing the single character and strings, and to clear the screen, we have also defined another function. Moving to the matrix keypad header files, this header file defined the macros and the functions for the 4x3 matrix keypad. The microcontroller we are using is a 4x3 matrix keypad. Here, the columns are taken as input and the data direction registers are defined here as trisby, and for the outputs, we are using the rows, and here trisby are defined for the data direction registers. So here also logic levels are defined as high and low. Moving to the next is the mode of scanning. There are two modes of scanning, state and the level. So when state is 1, it checks if any key is pressed or released, and level is 0, it means it identifies which row or column selection is active. And if nothing is no keys is pressed, it will return all release. It means that all the switches are at higher potentials. The function prototypes defined here as read matrix keypad. It scans the keypad and returns either key press state or key position. And the second one is the init matrix keypad. It configures rows as outputs and columns as inputs, as we already know. Coming to the microwave open header file, this header file will define the flags, macros, and the function prototype for the micro oven controller project. Coming to the screen navigation flags, there is a power screen which will show the power selection screen, then menu screen for the cooking menu screen, display time, pause and stop flags, and these are the flags defined for showing the time, pausing, and the stopping. Now there are fan control macros also we have defined. At RC2, and the data direction register we have defined, and on and off macros we have also defined. Next one is the cooking mode flags we have defined for micro, grill, and the convection mode flags. And there are other operational flags like as start mode, which begin cooking processes. There are also some reset flags required in the project. The first one is the reset flag, which resets the cooking time. I a new fresh start for the cooking time is given. And another reset flag is the reset nothing, which keeps the current time unchanged. The next function prototypes are display power screen, then display modes which shows the cooking modes, then set time which sets the time with reset option is also there, then display time which will display the time, then set the temperature which helps in setting the temperature, and heating the food which will start the cooking process. Next one is the CLCD header file. It contains all the actual logics to send the commands and data to the LCD in 4-bit mode. So here CLCD write function is defined where it sends the data in one byte to the LCD, or it splits the byte into two parts, 4-bit nibbles, higher nibble and the lower nibble. Here, register select option is used for the instruction mode or the data mode, and enable pulse is enabled to latch the nibble. And here, necessary delays are also being given according to the LCD timings mentioned in the datasheet. Also, we have defined here another function in a display controller, which runs the startup sequence required by the LCD controller in the 8-bit mode to 4-bit mode, and then two lines display. And this also includes the stabilization delays, and this was mentioned in the datasheet as well. Then there is a function initiated as in CLCD, which configure PIC pins, and it sets port D ports as outputs, and set the register select and enable inside output and calls any display control to initialize the LCD. The next one is CLCD PUTCH function, which moves the cursor to the specified LCD addresses and prints a single character at that position. And to print a string, we use CLCD print function, and to clear the screen, we use clear function. The next one is the ISR.c file, and this file is the implementation of the interrupt services routing for the microwave oven project. And here the function defined are void underscore underscore interrupt function. It is a special keyword which marks as a function of ISR, and it runs automatically when interrupts are enabled. And here static unsigned count is 0 is defined to accumulate the timer 2 ticks until 1 second is reached according to the program we will see. And if the timer 2 is 1, then is 1, the over flag interrupt flag is set. Now, in this part, if count plus plus equal to 20,000, it increments the count each time, and whenever it reaches 20,000, and this means that it is equivalent to the 1 second, and after that it will reset the count to 0. The countdown logic is shown as is as shown. If second is greater than 0, then it will decrement the counts. If second is 0 and minute is greater than 0, it will decrement the minutes and reset the second to 60. And it will also, and if the preheat time is greater than 0, then it will decrement the preheat time. And the timer 2 is equal to 0. This clears timer 2 interrupt flags to allow next interrupts. The next file is the matrix keypad.c file, and this file is the implementation of the 4 cross 3 matrix keypad. Here, the columns are configured as inputs, rows are outputs, and all the port B uh, all the port B switches are default to high when no key is pressed and sets all the rows high initially. Here, the scan keypad function is also there. It checks the column inputs to detect which key is pressed and returns the corresponding key. When no key is pressed, it will return all released, and it has also included small delays for signal stabilization. The next function defined here is read matrix keypad. It calls for scan keypad function to get the current key, and if mode equal to label, then it will return the row key, and if mode equal to state, and it will ensure that only one key is pressed, and if nothing is pressed, then it will return all released. Then coming to the microwave open.c file, and this implements the microwave open application logic, and here the display power screen will display powering on and the microwave oven message according to the sheet provided to us. Then the display modes will display the cooking modes as there are 4 modes we will be implementing in this project as micro mode, grill mode, convection mode, and start mode, and we will be seeing what are these modes. Also, the set time function is there, which allows the user to set the cooking time as so that they can cook the food according to their will. And there are also this program also supports blinking or the off blinking, which will represent that those fields are editable. And we have defined star for clearing the time and hashtag for starting the time, so that when the user will enter, it will start the cooking. And once the cooking will start, the fan will turn off, the timer to count starts its countdown, and the screen switches to the display time. Now, this display time function will show the current countdown in minutes and seconds on LCD and provides option for start, resume, pause or stop. So when the time reaches 0, the timer will get off, fan will get off, and the LCD will display time up. You can enjoy your meal and return, and it will get back return to the menu screen. Also, and one mode is there in which we will be setting our temperature, and it allows the user to set the cooking temperature, and it also supports the blinking, so that this will represent that those fields are editable. There also we have defined clear for clearing the temperature and hashtag for confirms that we have entered into the cooking mode, and it will start the preheating. And the cache temperature at 180 degrees Celsius is the threshold temperature we have set in the program, and preheating runs for 60 seconds. And after the preheat is over, timer will be off and it will return to the micro mode for time settings. So in the heat food function, default cooking mode will start and sets 30 seconds cooking time. and the timer 2 will start and the fan will get on. Next, coming to the timers.c file, and this file will configure a timer 2 on the PIC controllers. Here we have also defined the period register at 250. This 250 means that timer 2 will count from 0 to 250 before overflow, and the overflow event is used to generate periodic interrupts. This timer 2 equal to 1, it enables a timer to interrupt and ensures that when timer 2 overflows, the interrupt service routine will get triggered. Here we have initially made the timer 2 as 0 and we will turn it later on. In the main file, we have global variables defined as screen flag as power screen, which tracks the screen state is active or not. Then second and minutes we have defined. We have also defined reset flag, control whether cooking time and temperature should be resetted or not. We have also init config function in it, which will initialize the LCD keypad and the timer 2, and it will configure RC2 as output and sets it off initially. And also we have defined the global interrupts and the peripheral interrupts. In the main loop, it continuously reads the key, which key is pressed, and accordingly state is given, and accordingly the screen flag is gets updated according to the logic we have written in the program, and it and, uh, and when the program runs, it will start displaying the menu screen, and the key 1 will be pressed for the micro mode, key 2 will be pressed for the grill mode, key 3 will be pressed for the convection mode, and key 4 will be pressed for the startup mode. The micro mode. The micro mode is set for the cooking time, and reset flag ensures that it's reset only once. In convection mode, in convection mode we set the temperature to set the cooking temperature, and then the start mode we call the heat food function to begin the cooking, and the default is the 30 seconds. Later on, it can be increased. In the display time, we are showing the countdown in minutes and seconds. Here in the start mode, key 4 is pressed to add 30 seconds to it. Key 5 is used for pause, and key 6 will if key 6 is pressed, it will stop the cooking. And now we will be moving to our project, and these are the output we should get. Now I will show the simulation that how project is actually working. These are the first two modes, and this is the convection mode is being shown here. And now I will be starting the simulations. So let us start the simulation. So it has displayed powering on microwave oven with bars, and it is showing the cooking modes as micro, grill, convection, and start. Let us go with the micro mode. It is showing the power as 900 watts. Now we can set the time. Let us suppose we are setting here 9 seconds, and if we wanted to clear the time and reset the time, then we can uh, press on the star and we can again set the time. Let us suppose set us here 8 seconds and press enter. Hashtag is there for the enter, and if you wanted to pause, we will press 5. It has got pause, and if we again wanted to resume, we will press on 4. I have again paused it, and suppose if I press 6, then it will stop and it will get back to the menu screen. For that, I have to start it and pause. It has get back to the menu screen. Now let us go a bit deeper into it. I will set the time as 3 seconds and press enter, and the food is cooked. Time up, enjoy your meal. The second type of cooking mode is grill mode. Here also we can set the time, like let us suppose 5 seconds I have set, press enter. It will also start. It can also get paused, resume, and it can also get stop, and it will go to the menu screen. And here also it will display time up, enjoy your meal. The third one is the convection mode. In the convection mode, we can set the temperature or what temperature we want to cook our food. Let us suppose I have set it as 123 degrees Celsius, and if I wanted to change the temperature, then I will clear this and I will set up to some other temperature like 156 degrees Celsius, and I will press enter. Now it will start a preheating time. Here I will pause for a while, resume the video, ma'am. And now we can set the time for cooking. Let us set it as 5 seconds and enter. We can pause it also, resume it. When food will be cooked, it will time up and enjoy it. Now let us go to the last cooking mode, that is the start mode. It will it will go with the predefined 30 seconds of the timer here. And in this also we can start and resume. And if we click on 4, then it will add 30 seconds extra in it. And we can pause this and we can resume this. And again, if we press 4, then it will again add 30 seconds into it. It's going to up. It's a time up and we can enjoy our meal. This was our entire microwave oven creating the project. Coming to the development processes, we have begun our requirements with LCD display, keypad input, timer configuration, interrupt handling, and we have also implemented the logic whatever was used in our application microwave oven. We have also developed and tested each module. We have seen the outputs in the LCD driver. We have displayed messages. We have also taken input from the user, and the precise time period of 1 second was uh, very well developed. We have also implemented screen flags like power selection, cooking modes, time and temperature settings, and countdown displays. The next, we have implemented interrupt service routines programs, which has generated a precise timing of 1 second, and we have managed countdown logic and preheating duration. We have also integrated all the modules and we have responded to the user inputs. We have managed the countdown and we have also have good controlled fan operation. It was pausing and then it was again switching on. We have seen in the projects how we have implemented, and at last we have debugged all our codes in MPLAB ID with X8 compiler, and the final implementation was seen on the PIC16F877A development board using reliable performance, and we have ensured reliable performance. Now we will be looking at the tools used. We have used MPLAB XIDE, which is used for coding, compiling, and debugging in the language embedded C. We have integrated a compiler XC8 in this for PIC microcontroller, and with this ID has provided support for the register configuration and the peripheral interfacing. We have also used PIC 16F877A datasheet. We have referred for register settings, pin configuration, and peripheral details, and we have seen the output at the development board. This is the hardware platform for testing and running the microwave oven controller. And coming to the end of the video, I will be concluding the project. The internship at Emertxe has provided me a strong foundation in embedded systems and learning embedded. I have learned embedded C programming, microcontroller architecture, and peripheral interfacing. I've also designed and implemented a project, microwave oven controller project. Then I have also gained confidence in, so I have gained confidence in debugging and testing. And internship at Emertix has given me the idea from the demo focus projects to the real world embedded app applications, and this internship has prepared me for the future challenges in IoT and advanced embedded projects. So thank you for giving me this opportunity.